When we carry out a chemical reaction, we start with a finite amount of one or more reactants, and from that amount of reactants we can only make a certain amount of product. Now in reality, things usually don't go 100% smoothly. We usually lose some of our product, whether it's in transferring from one container to another, when we go to mass our final product, or there's a small spill, or a myriad of other things that could lead to us not obtaining the amount that we would predict that we should be able to get. And that's where percentage yield problem comes in handy. Percentage yield is oftentimes used as one way to gauge success in a synthesis reaction when we are trying to create a particular product. If we determine how much we should have gotten and compare that with how much product we actually did obtain, the higher the yield is, generally the better the process is for creating that product, but also the better our technique is. How mass stoichiometry problems integrate with percentage yield is these problems provide us with that theoretical amount, that if everything goes exactly according to plan, if no product was lost whatsoever, the maximum possible yield we should be able to get given the amount of starting materials. This is what the mass stoichiometry problem gives us. The percentage yield then again is going to compare that theoretical amount with the actual amount that is obtained in a given experiment. And so in equation form, percentage yield would be the actual amount or the experimental amount of product divided by the theoretical amount and then times 100. In the first practice problem, the actual amount of product in a reaction is 45.0 grams, although a mass calculation predicted 57.9 grams. What is the percentage yield of this product? Now, when solving percentage yield, you need to remember that the actual and the theoretical yields must be in terms of the same substance. If they're two different masses for two different substances, you cannot plug them directly into the percentage yield equation. In this case, we don't know exactly what the substance is, but we are told explicitly that there is an actual amount recovered, and a mass calculation gave us a prediction of another mass. So the 45.0 grams is our actual, that will be our numerator, and the 57.9 grams will be our theoretical yield, and thus our denominator. When we divide the two and then multiply it by 100, we should come up with a percentage of 77.7% yield. In this problem, we have a situation which is more realistic of the type that we would typically work with and find. What is the percentage yield in the following reaction if 5.50 grams of hydrogen reacts with nitrogen to form 20.4 grams of ammonia? And we see the balanced equation. Now the two masses that we're given, first inclination might be just plug those numbers into the percent yield equation and calculate. However, the two masses are for two different substances. And so with at least one of these, we're going to need to do a calculation at first. Now, percent yield is always in reference to one of the products. So the only product we have in this equation is the ammonia. So the 20.4 grams that is given for ammonia, that is going to be, in this case if we read the context, is going to be the actual yield. We started with 5.5 grams of hydrogen, and what we actually obtained in this situation was 20.4 grams of ammonia. So that will be the actual, and that will be the top part of our percentage yield equation. But that leaves the theoretical yield for us to determine. And that's where the 5.50 grams of hydrogen comes in. That is going to be our starting material, and what we need to calculate is, based on 5.5 grams of hydrogen, how much ammonia, NH3, could we potentially make? So we start with the 5.50 grams of hydrogen. First step is to convert that to moles. So we use the molar mass of hydrogen, 2.02 grams per 1 mole. Next, we need to convert from moles of hydrogen to moles of ammonia. So our mole ratio step will consist of 2 moles NH3 over 3 moles hydrogen. Remember that the numbers that we use in the mole ratio come directly from the coefficients in the balanced equation. And finally, we need to go from moles of our final material to grams of final material, grams of NH3, using the molar mass, which is 17.0 grams. When we calculate, we should come up with 30.9 grams of NH3. And what we need to remember is that this 30.9 grams is the theoretical yield. It's what would we get if everything went perfectly in the reaction, in the experiment. So now we need to take this theoretical amount and combine with the actual amount that was given in the problem, calculate 20.4 grams divided by the theoretical yield, which we just calculated, 30.9 grams, times 100, and estimating, we've got about 20 over 30, it's about 2/3, so we should be expecting an answer around 67%, and our answer does come out to 66.0%.